Mountain Bike Stepper Seatpost project, sponsored by Ben Lawler and Goddard Technologies. I'm the team leader, Kyle Golden. This is
David Goddard, Brian Ellett, Richard Fleck, Paul Boyer.
So Goddard Technologies is located in Beverly, Massachusetts. They specialize in mechanical and industrial engineering. They have a large range of products that they work on. Including like an air-powered ramp for law enforcement. They came to us with the Stepper Seatpost project to help them get the project off the ground before they move forward with it.
So I assume that everybody in here has ridden a bike and hit a bump. Now imagine coming down the side of a mountain on a rough trail at a high speed. So the solution to that would be a Stepper Seatpost that can adjust accordingly as you're coming down the mountain. As you can see in the top right figure, that the Seatpost will be lever activated and rise and be forced down by the pressure of the rider. So what's wrong with the current Seatposts on the market? They have pneumatic springs that they fail with mud and debris getting into them. They also don't work well in cold conditions. They're difficult to maintain and they can require special tools. So here's a comparison of some of the available Seatposts on the market. The average is about around $300. There are some outliers, but you're pretty much getting what you're paying for on those. So the project scope, the main goal was to design and construct a functional Stepper Seatpost, non-pneumatic, and our objectives were simple, easy to manufacture, keeping the cost under $200, minimize the total number of parts, and easy maintenance. We needed to provide our client with 2 functioning prototypes.
Alright, so our project constraints were as follows. The Seatpost travel range, or how far the seat itself can move up and down, had to be within a range of between 4 and 8 inches. The deepest that the Seatpost itself had to be able to be inserted within the frame of a bicycle was a depth of 12 inches. The outer diameter of the Seatpost had to utilize an industry standard of 30.9 millimeters, and the Seatpost had to be able to support a rider weight range of between 80 and 250 pounds. As a group, we wanted to keep the entire weight of the unit under 2 pounds, and we wanted to keep any seat rotation to less than 1 degree. So for idea generation, most of our brainstorming focused on the question of how do we lock this Seatpost in place after any adjustment has been made. So we came up with various brainstormed ideas and concepts and generated them as rough sketches to be evaluated by the group. Particularly good ideas were modeled up in SolidWorks to verify that they could be made within the dimensional constraints that our sponsor had requested of us at the time. And while we did that, we also considered important characteristics and qualities that we wanted out of our final design and weighed them based on their level of importance so that we could generate a Q chart to compare our concepts. So as you can see here, this is our Q chart, and basically how it works is that we took our top 5 designs and evaluated them all based off of our weighted criteria. From that, we generated a weighted score for each design, and what this weighted score allowed us to determine was which design came the closest to the needs that we had for our final design. And from that, we came to the conclusion that utilizing a pin slider mechanism for our locking device would be the best way to hold the Seatpost in place after any adjustment. We also came to the conclusion that for any testing that we would perform on the Seatpost, we would utilize an industry testing standard. It would be a ISO code used mainly for static testing on bicycle Seatposts, where the unit itself is mounted at an insertion depth of 3.5 inches and an angle of 73 degrees from the horizontal axis. From there, a vertical load of about 450 pounds would be applied to the topmost point on the Seatpost and maintained there for about 60 seconds.
So once we determined the design direction, the next step was determining the critical dimensions. So this was done by calculating the maximum stresses on the major load-bearing components. Once we had those stresses, they were compared with the respective material yield strengths to determine what the factor of safety would be. If the factor of safety that we calculated originally with those dimensions was within a range that we felt acceptable, we went back, made some modifications to the dimensions, and ran through it again until we were comfortable with the factor of safety. The next step was verifying these dimensions through simulation. So we did this by creating the geometry in console and applying the proper boundary conditions and loads. So here you can see a few examples of the boundary constraints that we used. highlighted in blue and yellow. Here are some of the results from the simulations we performed. You can see the high stress areas in red, where the low stress areas were also in blue. The maximum stress values from these simulations can be seen in the table below, as well as the maximum stress values from the hand calculations. And when we compare these two values, we found there was a maximum percentage error of roughly 2%. This gave us confidence with the dimensions that we had selected and allowed us to go forward with prototyping.
Now with the structural dimensions of our design finalized, we were able to finalize the mechanism that would activate the pin, as you can see here. And we began our prototyping and construction process of this design. Upon completion of the structural components of this design, it was discovered that the pin activation mechanism was overly complicated and would be very difficult to produce. So at this point, we determined it would be wise to redesign this mechanism. However, since all the structural components of the design would remain the same, we were able to actually start our structural testing at this point while we redesigned that pin. The main problem with this design was the activation cable was meant to go up and over that pulley and activate that pin, which would act against a spring. And that caused a lot of friction because it had to make that 90-degree bend right at the end of its travel. So we began our structural static testing. We had to go all the way down to the civil department to find a machine that was large enough to accommodate our needs and our loading range. So we were very thankful for Jeff Beaudry and his help with that. He was very accommodating. And as you can see, we have constructed our testing fixture to accommodate all the ISO standards of that test. And we did primarily a static test, as the dynamic test would be quite expensive, and this is just to prove out the design. So we applied our 450-pound load and held it for 60 seconds, and thankfully nothing went wrong. So as you can see, we did our math right, and we didn't have any unexpected failures. The way we collected data from this test was we used 2 dial indicators and a video capture system. That way we could log the load as opposed to the deflection of the seat post, both in the vertical and the horizontal direction. Then the main purpose of this data collection in this test was to both validate our simulations and to make sure we didn't have any unexpected failures of components that we hadn't considered. And as a result of this testing, we were able to compare and validate our simulations, giving us only a 3.3% error between our simulated deflection values and our actual experimental reported values. So this gave us great confidence both in our design and in our math that we did to create it. So as you can see here, we have our finalized design with the updated pin activation mechanism as modeled and as constructed. Right here is the heart of our new design. It's the pin activation mechanism. We have simplified it from originally 5 moving parts with a complicated pulley and a redirection of the cable, simplifying it to a straight motion of the cable, as well as only 2 major moving components. This design required us to revamp the housing block and change it out to those 2 pins, but it was actually much easier to construct these than the original part because it's only 2 straight holes and 2 cylindrical pins.
Here's a list of bill of materials along with the exploded view to the right-hand side of our product. The outer tube, the inner stanchion, the main housing, and the inner and outer plugs are made out of a 6061 T6 aluminum. The sleeve and the wedge pin are made out of Delrin, and the locking pin is made out of hardened 17-4 stainless steel. Overall, our product contains 19 unique parts. Here are some small batch manufacturing estimates. As you can see, with a small batch of about 10 seat posts, it costs about $300 per unit to manufacture. And however, if we decide to reduce the price by changing some of our non-critical components to a 3D printed part, it reduces the price down to $40 per unit. And if we decide to increase the batch size from 10 to 50, it reduces the price down even further to $160, which is below our $200 goal. Here is a list of all the items that we have purchased. The majority of the material that we bought was raw stock for developing and testing our product. We only spent 40% of our overall budget of $1,500 provided by the client. This leaves plenty of funds for the client to further take this product further in testing and manufacturing. As you can see, we completed our estimated
schedule and completed the project on time. The majority of the second semester was spent in the machine shop manufacturing parts and making sure everything worked correctly. So here's how we split things up. Kyle worked on all the CAD and produced calculations and simulations. David headed up machining and testing. I headed up physical testing and the budget. And Ricky and Paul worked on 2D drawings and helped in machining.
So throughout this process, we encountered a few problems that we had to overcome. The major one was that trying to reinvent the wheel is actually really difficult. Stepper Seatpost has been around for a while, and it's had a lot of people try to do it. So on multiple occasions, we actually ended up having an initial design we liked, did some further research, and found a patent that was kind of similar already, so it kind of ruled that out, made it difficult to go in that direction. On top of that, some of the steps in the process provided a pretty significant learning curve. So, for example, the machining process, we had to learn a lot. We were, we had to learn a lot. So, none of us had any real world experience in that. We were all basically novices. So, at the beginning, we did make a few errors and had some mess ups. Thankfully, Paul Sousa was there to help us out and kind of guide us and get us back on schedule. So, we were able to finish the project on time. And all in all, we think the project was a success. We were able to meet all of our goals and constraints. We got the total weight under 3 pounds, under 2 pounds at 1.7. We were able to get a travel range of 6 inches. We were able to reduce the part number over some of the competitors from 50 to 60 parts to down to 19. We were able to make the mechanism simple and easy for the average person to get into. You can repair the entire design with the removal of only 5 screws. And on top of that, we were able to get the price down below the $200 range, and we were able to save a lot of money on budget. And we'd like to thank everybody who helped us out, Professor Ferdous, Professor Foster, Paul Sousa, and especially our sponsor, Ben Lawler, who showed us the ins and outs of the industry and helped us get to where we are. Questions?